Okay, we've been talking solutions here. So a reminder, as we talked about, solutions is made up of two parts. There is the solute, which is the smaller part of the solution. There's the solvent, which is the larger part of the solution. And again, when you mix both of those together, you get a homogeneous mixture, which is a solution. And again, that is the ones that get the aqueous sort of symbol next to it. We talked about sort of the idea of like dissolves like. And that is the idea that the way that a molecule can interact with itself, and if it can interact the same way with another molecule, they will be soluble in each other. And that's those intermolecular forces. So you're looking for sort of similar interactions that they do with themselves, allows them to similarly interact with others. And what that gave us was sort of a few combinations that tend to be soluble, and that is our ionic things with polar, our polar guys with polar, and our nonpolar with our nonpolar. And the reason, again, these guys are able to sort of interact really well with each other is things that are ionic are charged ions, have positive and negative charges, and they work well with a polar molecule, which also has a positive side and a negative side to it because of the unequal sharing of electrons. All sort of ways that molecules interact with one another is almost a basic sort of opposites attraction. Positive side of one sort of molecule or ion is attracted to the negative side of another, and that's pretty much how all these work. Polar and polar things will use either dipole-dipole interactions or hydrogen bonding, which is a pretty strong intermolecular force. Nonpolar things will also be soluble in each other because, again, they will be using really similar type of forces, which are those dispersion forces, those kind of really temporary sort of weak forces. It's only when we sort of cross over between those two, when we kind of take something that's polar and nonpolar, that's going to give us something that's going to be insoluble in each other. And that's because they're trying to use really very different interactions. Something that's polar, again, going to try to use hydrogen bonding and dipole-dipole interaction, while something that's nonpolar is going to strictly be trying to use dispersion forces. And as we talked about last time, pretty much over the long period of time, there's no way for those interactions to basically be maintained. Because as dispersion forces are so weak, they're going to kind of break apart and not going to be able to still interact well with the polar molecule. We also talked about some concentration type units for solutions. We had percent mass to mass, which is our mass of solute divided by the mass of the solution times 100%. We also had percent volume to volume, which is the volume of solute divided by the volume of solution times 100%. And we had percent mass to volume, which is the mass of the solute over the volume of solution times 100%. So as we talked about, out of these three, this guy here on the bottom is one that you just have to sort of be careful of. It is very common that they will give you that information sort of separate from each other, as the solution is made up both of the solute and the solvent. So very common in those problems, they'll give you the solute and the solvent in different sort of values. And people commonly will use just the solvent rather than the entire mass of the solution. For the other two with the volumes, a lot of times you will be probably just given the volume of the solution, so you don't have to worry too much about that. But really, that mass one is the one you got to worry about. Those are some common sort of concentration units, but really the most common one is molarity, which is our moles of solute over liters of solution. And molarity can be thought of as a formula and sort of rearranged, where the liters would equal the moles divided by the molarity. And lastly, a very common one, moles is equal to liters times molarity. You want to make sure that whenever you're using molarity by itself, that you always sort of convert the volume to liters, because again, that will give you moles, which is probably what you're looking for in your calculation. If you take milliliters times molarity, you get what are known again as millimoles, which is probably not what you're looking for. So you'll be off by a factor of 1,000. So definitely want to always sort of multiply the molarity by the volume that's been converted to liters. That again is 1,000 milliliters is equal to 1 liter. The other important thing is usually when you do calculations involving molarity, as we talked about, it's a really good idea to get rid of the big M, because when people leave it in calculations, they very much sort of forget about the volume part, the liters part, not really sure where it is or even if it's there. And they start thinking to themselves that, oh, I'm just looking at the moles here rather than the molarity. So if you did have something like 1.25 molar sodium chloride, you can convert that into really a usable conversion factor by saying that that is 1.25 moles per liter. The number always stays with the moles part, and it's always per 1 liter. And you really can use it in dimensional analysis way and as a conversion factor by flipping it around if you needed to do so. And you could put it like this, but definitely when you do the calculations, you should convert it into both of these units here. That way you can see the units and hopefully won't forget about the liters part, which, as I mentioned, is a really, really common mistake that people make. Any questions on any of those things there? All right, so I think we did one at the very end there. So I think we're at this one here, which clearly I littered all over here. So let me erase all that off of that. All right, let's take a look at this one. What is the mass in grams of sodium nitrate that's required to make 2.5 liters of a 0.15 molar solution of sodium nitrate? Sodium is 2299. Nitrogen is 1401. And oxygen is 16. All right, so take a few minutes there, see what you come up with. Look for how many grams of sodium nitrate is needed here. Which is moles per liter. And in this particular case, we're looking for the grams of our sodium nitrate. We do have a volume given to us, which is 2.5 liters. We do have the molarity given to us of 0.15 molar. So if we're not sure, we do have molarity, we do have volume given to us. So it would make sense to solve for moles, as that's kind of the only thing we don't have. And that also makes sense since we're looking for grams in the end, because we can easily go from moles to grams, again, using our molar mass to do that from the periodic table. So to do this, our units of volume is good. It's in liters. I am going to convert that into a more usable sort of version, which is 0.150 moles per liter of our sodium nitrate. Once again, if you needed to, you could flip it around the other way. And now you can at least see both of the units that are present, so you don't forget about the liters part. So since we do have moles will equal liters times molarity, and once again, we want to make sure that's in liters. We'll take our liters, which is not that number, 2.5 liters. We'll do a little dimensional analysis here to get liters to cancel, which means we'll use it just like this. The liters here will cancel, and that's going to get us 2.5 times 0.15, 0.375 moles of sodium nitrate. That again is close to what I'm looking for, but I am looking for how many grams. So we would need to go to the periodic table and figure out the molar mass of our sodium nitrate. And in this case, there is one sodium at 2299. There's one nitrogen at 1401. And there are 3 oxygens at 16 for our sodium nitrate here. That's going to give us 85 grams per mole as the molar mass of our sodium nitrate from the periodic table. So the last step here would be to take our moles, use our molar mass really as a conversion factor to get to grams. That means the 85 grams need to go up on top. The moles need to go on the bottom. The moles will cancel here, and we will end up with about 31.9 grams of sodium nitrate in this case. So first off, any question on the calculation there? So this number represents that if I wanted to make the solution, I would go and weigh out 31.9 grams of sodium nitrate. And since it's ionic, probably some water would be a great solvent in this case. Put it in some water to get it to dissolve, top it off to a total volume of 2.5 liters, mix it up really good. And now I should have a solution that has a molarity of 0.15 molar. Any questions on that there? 3 sig figs pretty much, because it's 3 sig figs everywhere in that problem. So that's probably what we're going to end up with here in terms of our answer. Any questions on that one? Okay. Now let's take a look at another one here. Something else that we also talked about last time was the idea that with ionic compounds, especially with solutions, sometimes we are interested in maybe just the concentration of the ions that are floating around in the solution. Because it is a solution, pretty much they're ionic, which means that those ionic guys are going to break apart into the cations and anions as they're floating around. So why don't you take a moment here, and for each of these separately, we're looking for what is the concentration of the individual ions that make up each of these solutions. So in the case of the first one, what is the concentration of the sodium ion that's there and the sulfate? For the second one, what would be the concentration of the potassium and the chromate? Okay, so let's take a look. So as we talked about last time, when we have something like these ionic compounds that are in solution, because they're strong electrolytes, they are going to 100% break apart into the ions. So that's what you want to think about when we're trying to figure out the concentration of the individual ions, is how this guy is going to kind of break apart in solution. And when he does, we will get a couple of sodium ions floating around, and we will get basically one sulfate ion floating around. So when we dump that into this solution, we got these sodiums and we got a sulfate basically floating around in that solution. So if we know the concentration of the whole thing here, we talked about a couple of ways you could figure out the concentration of the individual ions, but probably the easiest and really the fastest way to do it is kind of like stoichiometry here. What we see here is for every one of the whole things, we get 2 of the sodium ions floating around. So it's really twice as concentrated in terms of the sodium ions. So how that affects concentration is we actually would just take 2 times the concentration of the whole thing. And that would tell us that in that particular solution, the sodium ions would have a concentration of 2.4 molar. And we could do the same relationship, or find the relationship between the whole thing and sulfate. And we see that it is a 1-to-1 relationship between the whole thing and sulfate, which means in this particular case, we would take 1 times the concentration of the whole thing. And that would give us a concentration of 1.20 molar. And that would be for our sulfate ions that are floating around in that solution. As we talked about last time, obviously it's not additive, so 2.4 and 1.2 doesn't give us 1.2. It is sort of proportion-wise of what you get, and just visually looking at what I drew up here, we get pretty much twice the amount of sodium per sulfate that goes in there, so it's twice as concentrated in terms of the concentration of the sodium ions versus the sulfate ions. Any questions on that? That again is sort of, as we talked about last time, the calculation. Once again, if you were looking at sort of the longer version of that calculation, you would take the 1.2 molar and convert it to moles per liter of the whole thing. And then you would just do a little stoichiometry. 1 mole of the whole thing gives us 2 moles of sodium ions. And that again is why we are multiplying by 2 here. And that will get you your 2.4 moles per liter of sodium ion. So that's the longer, really kind of dimensional analysis, stoichiometry calculation of it. But again, the quick way is really just to multiply it by the coefficient there, and you'll get the same answer, obviously, either way that you do it. Question on that one there. We would obviously do the same thing here for our second solution and just really sort of figure out how it breaks apart. And in this case, we would have our potassium chromate, which should be soluble because it has potassium in it. Gives us 2 potassium ions and a chromate, -2 charge. Once again here, the whole thing is 0.75 molar. Doing our same sort of reasoning, a 1-to-2 relationship there for our potassium. So we will multiply the concentration by 2 to give the appropriate concentration of our potassium ions, 1.50 molar of potassium. And again, it is a 1-to-1 relationship between the whole thing and the chromate. So taking our concentration and multiplying it by 1, going to give us 0.75 molar of our chromate in this particular solution. So once again, here it's kind of similar. We get basically twice the amount of potassium as we do for chromate for every one that goes in for a swim. So the concentration of potassium is going to be twice that of chromate that's floating around. Any questions on how you relate the whole concentration to individual ions? And that's a very common sort of thing. Sometimes you are interested in, especially with solutions, maybe just the ions that are floating around, not necessarily the whole thing. Any questions? All right, so why don't you try one here for this particular one? We're looking for how many moles of calcium ions and chloride ions are present in 42 milliliters of a 0.35 molar calcium chloride solution. Okay, so let's take a look. So really there's a couple of approaches you could take to this problem. You could just work with the calcium chloride together, and then at the end sort of relate it to the individual ions through sort of stoichiometry. You also can, since you have the molarity of the calcium chloride, just right off the bat get the molarity of each of the individual ions, and then just kind of work the problem at that point. So that's how I'm going to do this problem, since I do have the concentration of the whole thing, and I can figure out how this guy breaks apart. When we have a calcium chloride solution, which would be aqueous because of the calcium and the chloride coming together, and we will have a calcium ion and 2 chloride ions. So once again, just like we just previously did in the last problem, because we know the whole concentration here of the calcium chloride is 0.35 molar between the whole thing and just the calcium ions by themselves, it is a 1-to-1 relationship, which means really the concentration remains the same. And we would have a concentration for calcium of 0.35 molar. We also could do the same thing between the whole thing now and our chloride ions, and it's a 1-to-2 relationship, which means we will take the concentration and multiply it by 2. And that's going to give us 0.7 molar as the concentration of our chloride ions. So now that I have the concentration of each of the individual ions, I can really just use the molarity equation and figure out how many moles we would have of each of them. Once again, our molarity here is moles per liter. So now that I have the molarity, I have the volume, which does need to be converted to liters. So we do want to do that as well. So we're going to take our 42 milliliters, 1,000 milliliters in a liter. Going to give us 0.0420 liters. So now if I take my calcium, I'm going to take my volume, which is 0.0420 liters. As if I solve for moles, it is liters times molarity. I am going to get rid of the big M here and use it like we talked about as 0.35 moles per liter of calcium. Again, that's what the big M will represent. And you do more of a dimensional analysis approach here of 0.350 moles per liter of our calcium ion. These guys are going to cancel, and that's going to get us 0.0420 times 0.35. 0.0147 moles of calcium would be floating around in that solution. We could also here do the exact same calculation for our chloride ions. So our chloride ions here, we'll use the same volume as it's in the same beaker or whatever it may be. Once again, I'm going to turn this big M into a usable sort of calculation, which is 0.7 moles per liter of chloride. So using that, 0.7 moles of chloride per liter. Liters will cancel. Going to give us 0.0294 moles of chloride. As you can see there, because it is twice as concentrated in terms of the chloride, we have twice as much moles of chloride floating around in that solution as we do of the calcium in this particular case. Any questions on that calculation there? Again, as I mentioned before, you could have used the volume here, and again, the molarity of the whole thing, and got the moles of the calcium chloride, and then just did the 1 mole to 1 mole relationship, or the 1 mole to 2 mole relationship, and you would get the same answers as well. Question on how to figure out concentration of ions in solution. Again, kind of important, as in some cases, that's what things people are interested in. It's just the individual ions floating around. Question on molarity. All right, then the next thing we're going to talk about is dilutions and making dilutions and how to calculate that. So when we take or make a dilution, usually this is a case where we have a more concentrated solution, and most solutions come more concentrated when you buy them. They're sometimes referred to as stock solutions, and usually when we use them, say in the lab or something like that, we oftentimes want to use a more dilute solution than something that's really, really concentrated. So something that's a dilute solution will have a relatively small amount of solute versus in the solution, versus something that's more concentrated, which will have a larger amount of solute. The reason that's important is when you do a reaction with solutions, it is the solute that is really doing the reacting. So later when you do like your hydrochloric acid and your sodium hydroxide titration, it is the sodium hydroxide and the hydrochloric acid that's reacting. All that water and extra stuff that you put in there doesn't really matter because it's not doing anything. It's really the solute in those cases, which is why when you use the volume for your calculations, you use the volume of the HCl you added, 20 mils, not like the total volume of 50 mils when you put the water and all that kind of stuff in there. So when we do a dilution, oftentimes the only thing that is added is more solvent. And in a lot of cases, most common sort of solvent used in a lot of situations is water. But again, it doesn't always have to be water as a solvent. So when we add more solvent to do a dilution, what ends up happening is the moles of the solute before and after the dilution remain the same. They do not change. But the molarity of that solution does go down. And the reason why the molarity of that solution goes down is found in actually the molarity formula, which is moles of solute divided by liters of solution. And remember that the solution is the solute and the solvent. So technically speaking, when you go and add more water or solvent, what you're actually doing mathematically speaking is adding more of the bottom number. So you're really just increasing the solvent, which if we look at the molarity equation means that the bottom number is going to get larger. And when the bottom number gets larger, if you divide by a larger number, your molarity here will go down. So that is why the molarity actually goes down, because you're adding more solvent, increasing the volume of the solution, and that will then bring down your total molarity. But the moles remains unchanged because we only added solvent. We didn't add any more solute in either case. And again, that means that that remains the same regardless of how much you put in there. So kind of the example we did, I think, of the soda where you got all the ice that starts to melt. And at the end, you still have the same amount of sort of soda, syrup, and stuff in your cup. You just now have a lot more water with it, which makes it much more dilute than it was, obviously, fresh from the fountain and stuff like that. So when we do a dilution, there's a couple of ways we could do a dilution. Fancy way is using a volumetric flask. So that is a volumetric flask. The word volumetric usually means expensive, so you shouldn't break those things. But they usually also means that it usually has just one marking on it. And that one marking, for example, represents the volume of this flask. And usually when you're doing anything with volumetric, usually that's like 2 decimal places is usually where you go to. So this would be really 500.00 milliliters. And what you could do is add a little bit of water first, take your more concentrated solution here and add it, and then top it off with water till you get to that line and give it a nice mix. And now you'll have a more diluted solution there on the right-hand side than what you started with. By the way, if you go over the line, can you just dump it out back to the line? Would that be okay? You cannot, because your solute, right, is dissolved in it, right? And when you would dump out that liquid to get it back to the line, you're actually dumping out your solute, which means your molarity will no longer be the same as what it was to begin with. So you can't just kind of dump it out if you go over. That's why when you use this, usually you want to be really careful. Use a wash bottle, maybe a medicine dropper towards the end there to make sure that you kind of dial it into that line. Now, when we do a calculation for a dilution, we typically will use this equation here, which is M1 V1 is equal to M2 V2. And this is molarity and volume equals molarity and volume. So this is usually before the dilution. So that's usually the more concentrated solution. This is usually the more dilute solution on this side. Now, out of these formulas, when you're dealing with molarity and volume, this is the one formula where it really is okay if you do want to leave the volume in milliliters. It will work fine with molarity because all the units will cancel out correctly. So what I mean by that is, for example, here, if you were going to solve for M2, it would be M1 V1 divided by V2. And in this case, if you did molarity times milliliters divided by milliliters, they cancel out and you'll be back to molarity. So if you're going to use a dilution equation, you can use it in milliliters. And that's really because you're going to be dividing by milliliters. So you're back to when you take milliliters times molarity, that gives you millimoles divided by milliliters. The millis cancel, brings you back to moles per liter, which is molarity. So this is the one case where you can leave it in milliliters on both sides and you'll be okay. If you are not using this equation, if you're not doing a dilution, you should definitely, bless you, convert it to liters and times it by the molarity. Also in this equation, if you're not sure, you could also convert it to liters and it'll work out okay, but you can do that in this particular case. M1 is usually, again, the concentration of the more concentrated solution. V1 is how much of that more concentrated solution you would be taking out to make your solution. So for example, if I had a solution over here that was, say, 20 molar, and I wanted to make another solution over here that was, say, 0.5 molar. When I solve for V1, that would be how much I would take out of my more concentrated solution to put into my new beaker, whatever you're making. V2 is our final volume, right? And so what's the rest of the volume going to be is actually, in a lot of cases, water that you're going to add to do that. And a lot of times when we do a dilution, they sometimes will ask how much water that you want to add. And that usually is your V2 minus your V1 situation. And that's because your V1 is how much of the more concentrated you put in there Your V2 is your total volume you want to end up at. So you do want to subtract it to figure out how much solvent or water to add. And the example of that is, for example, let's just say we took 10 milliliters out and we wanted a final volume here of 100 milliliters. So when I would put my 10 milliliters in here to do my dilution, should I put 100 milliliters of water in there with it? I should not, because if I put 100 milliliters of water plus the 10 milliliters, my total volume now is 110 milliliters, which is more than what I want. I want only 100 milliliters total. So the amount of water would actually be 100 minus 10, which means I should throw in there 90 milliliters in this made up example of water. And that would give me a total volume of 100 milliliters. And when I mix it together, I would then have the correct concentration that I'm looking for. So in this case, we would take 100 minus 10, and that would give us our 90 milliliters of water that we would add in this case. So a lot of dilution problems, very common question is that, not necessarily, V1 or V2 or something like that, but, how you would make the solution, how much water that you need to add. Now, I would say probably 9 times out of 10 people will probably use this equation because frankly, molarity is the most common unit of concentration that you have, but books and people will sometimes use C1 V1 is equal to C2 V2, and it really is the same equation. C here is just generic for concentration. So technically speaking, you can use any concentration unit you want, although molarity is the most common unit, and that's why most people use M1 V1 equals M2 V2. You could do this with percent mass to mass on both sides, percent volume to volume on both sides, percent mass to volume, any other type of concentration unit on both sides of that. So you'll sometimes see this equation written as C1 V1 equals C2 V2. You also sometimes mistakenly perhaps see this equation used as the titration equation, and it's really not, it's the dilution equation. And some people call that the titration equation, and it only works in a very specific situation. Otherwise, if you do not have a one-to-one relationship between your acid and base, you will not get the right answer if you use that equation. So you should do those sort of problems through stoichiometry and not use that equation, which sometimes people will use for titrations in the wrong situation, and you'll get the wrong answer. So just keep that in mind when you do those type of calculations. You should do more of a stoichiometry calculation in any type of titration problem, because it's really just a solution stoichiometry type problem. You shouldn't really use that. You should really only use this equation for dilutions. It's really the proper place for you to use it for. Any questions on that there? All right, I think we will lay